Better believe it, that is smudge here. So, truth be told, we're examining fundamentally the earliest structures we know in the universe, and this sort of information is coming in a fraction of the time we expected. I think a lot of the records we have in the current-day universe are going to be broken very soon. A notable Nobel Prize winner says that the James Webb Telescope has recently found something odd in the universe, and the changes coming may be more than we are prepared for. The most recent discoveries are challenging established science. Increasingly bizarre things are occurring since James Webb has uncovered a new effect that's turning our physics books on their heads. Adam Rees, an astronomer and Nobel Prize winner, has long thought that science is on the verge of crisis. There are heaps of inexplicable problems that are growing bigger every day. Can we still figure out what's going on, or is the field of science over? Adam Rees is likely one of the few experts who is staying calm nowadays. Things are no longer the same as they were before the James Webb Space Telescope was launched. It's likely that the universe is much older than we thought. Galaxies have formed much faster and in vastly different ways than we expected, and the universe may not be expanding from a single point. What should we do now if dark matter was simply a mistake and James Webb is already showing us a new picture of strange things happening in the universe? One of the most knowledgeable people in the field of studying the universe's expansion is Adam Rees. His work, which revealed that the universe is expanding faster than we thought, significantly changed the way we think about the cosmos and was a major part of the Hubble effort. Having worked hard for many years, Rees knows that our understanding of the universe is flawed, so he is excited about what the telescope has recently discovered. He helped examine the universe using supernovae as standard candles for the first time. Researchers use cosmic scales to measure how far things move and how fast they move. Standard candles, such as Type Ia supernovae, provide highly accurate measurements. However, there was still one issue. Rees and his team found that the universe was expanding at different rates in different areas, which was unexpected. During their work, another discrepancy became clear. Rees's measurements were significantly different from those based on the redshift method, which was surprising. We now refer to these differences as the Hubble tension. Their work was so impressive that Rees, alongside his colleagues Saul Perlmutter and Brian Peig-Schmidt, won the Nobel Prize in Physics in 2011. They won for discovering that the universe's expansion rate is accelerating rather than slowing down, as was previously thought. Both Schmidt and Rees are part of the High-Z supernova search team, which is exploring ways to improve distance measurements in the universe as part of the Supernova Cosmology Project. Perlmutter, on the other hand, came to similar results around the same time. They observed Type Ia supernovae, which are extremely bright stars that explode and are an excellent way to determine how far away things are in the universe. These findings surprised everyone by showing that the universe's expansion rate is accelerating, contrary to the previous belief that it was decelerating due to the gravitational pull of matter in the universe. The notion of an isotropic universe, one that looks the same in every direction, seems increasingly untenable as our understanding deepens. The universe is proving to be far more complex than we initially thought. The most concerning issue in current science is that researchers and cosmologists are being presented with new inquiries and stunning realities. The possibility of an isotropic universe is beginning to fall apart, taking with it one of the most significant concepts about our universe. Regardless of what direction you look at the universe from, isotropy suggests it appears the same. A central piece of the cosmological principle says that, if we examine the universe on a large enough scale, it is uniform and homogeneous. For example, the pattern of cosmic microwave background radiation seems to be similar everywhere, and large clusters of galaxies are spread out evenly in space, or at least that was how it appeared in the past. Researchers then transformed these observations into simple mathematical rules to make sense of the world. However, this may have been a poorly conceived idea. Adam Rees and other researchers studying accelerated expansion initially supported the isotropic model because measurements of supernovae showed that the rate of expansion appeared consistent. It seemed like there was some form of isotropy. However, the expansion is occurring much faster than older physical theories predicted. Currently, the mystery of dark energy is extremely intriguing. We need to learn more about dark energy to solve the riddle of new cosmology. We still don't know what this energy is made of, but understanding that it exists and its effects is crucial for figuring out how and why the universe expands in an isotropic manner and how the current standard model of cosmology came to be. Dark energy is theorized to be a form of energy that could exist throughout the universe. It is thought to be a key component in the current theory of how the universe is expanding, countering the force of gravity and accelerating the universe's growth. According to the current cosmological model, dark energy makes up about 68% of all the energy in the universe. This presents an issue. Scientists say that an unproven energy form accounts for nearly 70% of the energy processes in the universe. The observation of Type 1a supernovae by Adam Rees and his colleagues was crucial evidence for the existence and properties of dark energy. To date, the rapid expansion observed couldn't be explained without a powerful force pushing against it. The cosmic microwave background radiation and other large-scale structural investigations have shown that this hidden energy is genuinely real. However, new findings by the James Webb Space Telescope has led individuals to question the possibility of dark energy. The JWST can observe the early universe with more precision than was conceivable before. The standard model of cosmology suggests that structures and objects should appear younger and less developed than when initial detailed observations were made. These findings might indicate that the universe could have started earlier or expanded significantly faster than previously thought. Before these discoveries, we believed we fully understood certain major cosmic components and forces, like dark matter and dark energy. This could imply that the current model of the universe may need to be completely reconsidered. Although we're not ready to develop new theories yet, we cannot create new hypotheses since we still don't know enough about what's happening. Will the universe of quarks hold the answer? We'll have to wait a bit longer to change our understanding of the world. We won't be able to form a new picture until the JWST sends more images, and scientists make even more astonishing discoveries. This process could take some time. In the meantime, researchers worldwide are searching for solutions that currently seem out of reach. David Gross is another scientist excited about this challenge and sees it as an opportunity. Gross suggests that the answers to the universe's big questions lie not in the big picture but in the small picture. As a prominent theoretical physicist and a Nobel Prize winner in 2004, he has a deep understanding of string theory and the concept of strong forces. He received his Nobel Prize for discovering asymptotic freedom in the theory of strong interactions, a breakthrough critical to understanding how quarks behave. Quarks are the building blocks of protons and neutrons, and the standard model of particle physics is based on these particles, which form the foundation of everything we can see and measure in space. Thus, the fundamental structures and laws of the cosmos should also exist in the subatomic world. Among other things, Gross contributed ideas about what happened immediately after the Big Bang. During that time, there were no stars or other entities in the universe. For hundreds of thousands of years, there was just a very hot primordial soup where particles could move around without sticking together. It's likely that before the Big Bang, there was only a kind of quantum transition in which all forms canceled each other out to the point of effectively being zero. This quantum fluctuation unraveled with the Big Bang, with particles full of charges and forces bursting into a space that hadn't existed before. Over time, these particles formed galaxies, planets, stars, and life forms like us. Should we believe Gross when he says that these particles hold all the answers? Quite possibly. But how can we study the behavior of particles from 13.8 billion years ago? One tool scientists use is the microwave background energy from space, believed to be an excellent representation of what happened shortly after the Big Bang, though it has likely changed since then. Quantum physicists and classical physicists don't fully agree on how to interpret this record of the early universe, and in the scientific community today, quantum mechanics, particle physics, and standard cosmology have not been unified. Quantum mechanics doesn't align with our understanding of created matter, which means the missing link could be found in quantum physics. David Gross is confident that this link can be discovered within particles and forces that were previously unknown. He was one of the experts who brought together people from different fields to reach a consensus before the James Webb Telescope began this discussion. Gross worked hard to connect quantum physics and general relativity, which he co-authored, to bring them together. He aimed to bridge the gap between these two scientific fields. Gross's work on asymptotic freedom shows how particles behave when their energies are extremely high, which is essential for understanding the early universe immediately after the Big Bang when energies were very high. His theories could help us understand parts of cosmic evolution that remain unclear. However, there is some disagreement among scientists because many traditional physicists believe that ideas from string theory are too hard to accept. David Gross thinks the quantum fluctuations in the cosmic microwave background hold the answers to all the questions that remain unresolved. The cosmic microwave background, CMB, can be seen everywhere in the universe. From 1989 to 1993, the Cosmic Background Explorer, COBE, satellite orbited and was the first to observe small temperature fluctuations in this radiation. The Wilkinson Microwave Anisotropy Probe, WMAP, analyzed these changes from 2001 to 2010 to check if they showed evidence of the Big Bang. The Planck satellite recently created one of the most detailed maps of the CMB yet, but scientists still aren't sure how to analyze this data. Some researchers claim to have found evidence of the Big Bang in the CMB, while others believe it suggests interactions with other universes and the existence of a multiverse. Join the community now and be part of every new video.